The Big Bang Theory is our best attempt to explain the origin of the universe. It is a cornerstone of modern cosmology, providing a framework for understanding how the cosmos has evolved over billions of years. This theory is supported by a wealth of observational evidence, including the cosmic microwave background radiation and the distribution of galaxies in the universe. It suggests that the universe began from an extremely hot and dense state about 13.8 billion years ago. This initial state was unimaginably hot and dense, a singularity where the laws of physics as we know them break down. From this singularity, the universe began to expand and cool, leading to the formation of the first subatomic particles and simple elements. This wasn't an explosion in space, but rather an expansion of space itself. Imagine space as a balloon being inflated, with galaxies like dots on the surface of the balloon moving away from each other as it expands. This analogy helps us understand that it's not galaxies moving through space, but space itself that is expanding. Imagine a tiny, incredibly hot speck, smaller than an atom, suddenly expanding outward. This rapid expansion, known as cosmic inflation, occurred in a fraction of a second, exponentially increasing the size of the universe. During this brief period, the universe grew from subatomic scales to macroscopic scales, setting the stage for the formation of all known structures. This expansion continues to this day, pushing galaxies farther apart. Observations of distant galaxies show that they are moving away from us, with more distant galaxies receding faster than those closer to us. This phenomenon, known as Hubble's law, provides strong evidence for the ongoing expansion of the universe. The early universe was a chaotic soup of energy. In this primordial state, temperatures were so high that particles could not combine to form atoms. Instead, the universe was filled with a hot, dense plasma of quarks, gluons, and other fundamental particles, constantly interacting and colliding. As the universe expanded and cooled, this energy began to condense into matter. This process, known as nucleosynthesis, occurred within the first few minutes after the Big Bang, leading to the formation of the first protons and neutrons. These particles eventually combined to form the nuclei of the simplest elements. First came elementary particles, the building blocks of everything. Quarks combined to form protons and neutrons, while electrons remained free until the universe cooled further. These elementary particles are the foundation of all matter in the universe, from the smallest atoms to the largest galaxies. Then, protons and neutrons formed, followed by the simplest atoms, hydrogen and helium. These light elements were the first to form as the universe continued to cool. Hydrogen, the simplest and most abundant element, became the building block for more complex structures. Over vast stretches of time, gravity drew these atoms together. Gravity, the force that attracts objects with mass, played a crucial role in shaping the universe. It caused hydrogen and helium atoms to clump together, forming vast clouds of gas. This created giant clouds of gas, which eventually collapsed under their own weight, igniting into the first stars. These stars were massive and short-lived, burning through their fuel quickly and ending their lives in spectacular supernova explosions. These stars, much larger and hotter than our sun, lived fast and died young, seeding the universe with heavier elements. The supernova explosions scattered these elements into space, enriching the interstellar medium with the building blocks for future generations of stars and planets. From these stellar explosions, new generations of stars and galaxies were born, eventually forming the universe we see today. The cycle of starbirth and death continues, driving the evolution of the cosmos and creating the diverse array of celestial objects we observe. The Big Bang model offers a compelling explanation for the universe's evolution, but it's not without its mysteries. Questions remain about the nature of dark matter and dark energy, the ultimate fate of the universe, and what, if anything, preceded the Big Bang. As our understanding of the cosmos deepens, we continue to uncover new insights and refine our theories, bringing us closer to unraveling the profound mysteries of the universe. If the Big Bang happened, we should be able to find remnants of its incredible heat. This heat would have cooled over billions of years, but it would still be detectable as a faint glow permeating the universe. In 1964, Arno Penzias and Robert Wilson accidentally stumbled upon just that. the Cosmic Microwave Background, or CMB. They were using a radio telescope to map the sky when they encountered a persistent noise that seemed to come from every direction. This faint afterglow permeates the universe, a whisper of radiation left over from the Big Bang. It's like a cosmic fingerprint, a relic from the time when the universe was just a baby. Imagine the universe just 380,000 years after the Big Bang. At this stage, the universe was a hot, dense plasma of particles, primarily protons and electrons. It was a hot, dense fog of protons and electrons, too thick for light to travel freely. Photons, or particles of light, were constantly being scattered by these charged particles, making the universe opaque. As the universe cooled, these particles combined to form neutral hydrogen atoms, allowing light to finally escape. This event is known as recombination, and it marked a significant turning point in the history of the universe. This first light, stretched over billions of years by the expansion of space, is what we detect today as the CMB. The light has been redshifted to microwave wavelengths, making it visible to radio telescopes. It's a snapshot of the universe in its infancy, a baby picture of the cosmos. By studying the CMB, scientists can learn about the conditions of the early universe and how it has evolved over time. The CMB tells us a lot about the early universe. For instance, it reveals the density and composition of the universe at that time, as well as the rate at which it was expanding. Its uniformity suggests that the universe was remarkably smooth at its beginning. This smoothness is a clue to the processes that governed the early universe, such as inflation, a rapid expansion that occurred fractions of a second after the Big Bang. However, tiny temperature fluctuations within the CMB provide the seeds for the large-scale structures like galaxies and galaxy clusters we see today. These fluctuations represent slight variations in density, which over time led to the formation of the complex cosmic web of matter that makes up the universe. By mapping these fluctuations, scientists can trace the history of the universe from its earliest moments to the present day. The CMB is not just a relic of the past. It's a tool that helps us understand the fundamental nature of the cosmos. Modern telescopes and satellites, like the Planck satellite, have provided us with incredibly detailed maps of the CMB. These maps have helped refine our models of the universe and have led to new discoveries about its age, composition, and ultimate fate. The study of the cosmic microwave background continues to be a vibrant field of research, offering new insights and posing new questions about the universe. It's a reminder of how far we've come in our quest to understand the cosmos and how much more there is still to learn. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He was working at the Mount Wilson Observatory in California, using the most powerful telescope of his time. Hubble's observations would forever change our understanding of the universe. He observed that galaxies are moving away from us, and this movement wasn't random. It followed a specific pattern. The farther away a galaxy is, the faster it recedes. This was a monumental discovery because it suggested that the universe itself was expanding. This observation, known as Hubble's law, provided the first evidence that the universe is expanding. Hubble's law states that the velocity at which a galaxy moves away is directly proportional to its distance from us. But how do we know galaxies are moving away? The answer lies in the light they emit. Light from these galaxies travels through space and reaches us here on Earth. By analyzing this light, astronomers can determine various properties of the galaxies, including their speed and direction. As light waves travel through space, the expansion of the universe stretches them out, shifting them towards the red end of the spectrum. This phenomenon is called redshift. Redshift occurs because the wavelength of the light is stretched, making it appear redder than it actually is. The greater the redshift, the faster the galaxy is moving away from us. This relationship allows astronomers to measure the speed at which galaxies are receding and thus understand the rate of expansion of the universe. Imagine baking a loaf of raisin bread. As the bread rises, the raisins move farther apart. This is a simple analogy to help visualize the expanding universe. As the bread rises, the raisins move farther apart. Similarly, as the universe expands, galaxies move apart from each other. The space between them stretches, just like the dough in the bread. Similarly, as the universe expands, galaxies move apart from each other. This expansion is not due to the galaxies moving through space, but rather the space itself expanding. The redshift of light is like the stretching of dough between the raisins. As the dough stretches, the raisins move apart, and as the universe expands, the light stretches, shifting towards the red. It's a visible consequence of the expanding universe. This stretching of light provides a direct observational method to study the expansion. Hubble's discovery revolutionized our understanding of the cosmos. Before his work, the prevailing thought was that the universe was static and unchanging. It provided the first observational evidence for the Big Bang theory, suggesting that the universe had a beginning and has been expanding ever since. Hubble's work established the foundation for modern cosmology. Today, astronomers continue to build on his legacy, using advanced telescopes and technology to explore the vast, ever-expanding universe. So, did the Big Bang really happen? The universe still holds more questions than answers. And we're just getting started. If this cosmic mystery blew your mind, don't forget to hit that like button. It really helps more curious minds like yours discover this video. Subscribe and ring the bell so you never miss our next deep dive into the unknown. We explore the strangest corners of space, science, and everything in between, almost daily. Got your own theory? Or want us to explore another cosmic mystery? Drop it in the comments below. I'm reading every one. And if you're ready for more, check out the rest of my videos where we explore what scientists aren't telling you about space. Thanks for watching. Stay curious and keep looking up.